One of the more perplexing and underrecognized aspects of vitamin B12 physiology is the phenomenon of neurological damage occurring even when blood levels of B12 appear normal. This contradiction has puzzled clinicians and researchers alike and reveals a deeper layer of complexity surrounding how B12 functions at the cellular level. It suggests that serum B12 measurements may not always reflect true intracellular sufficiency, and that deeper biochemical disruptions, such as poor transport, impaired receptor function, or accumulation of inactive B12 analogs, can lead to nerve damage in the absence of any apparent laboratory abnormality. The standard serum B12 test measures total cobalamin in the blood, including both active and inactive forms. However, only a small fraction, roughly 20–30%, is biologically active as holotranscobalamin, the form of B12 that is actually delivered into cells. The rest circulates bound to haptocorin, a binding protein that does not facilitate cellular uptake. In individuals with normal serum B12 levels but low holotranscobalamin, tissues may still be functionally deficient. This is especially dangerous in the nervous system, which depends heavily on B12 to maintain the methylation cycles that support myelin synthesis, neurotransmitter balance, and DNA repair. When these processes are compromised, neurological symptoms can arise, even in the face of seemingly adequate lab values. Further complicating the picture is the presence of B12 analogs, molecular mimics of the vitamin found in certain foods and especially in poorly absorbed supplements or fortified products. These analogs can compete with active B12 for transport and receptor binding, essentially blocking access to the real thing. Some plant-based sources, for instance, contain pseudo B12 forms that are structurally similar but functionally inactive in humans. This means that individuals relying heavily on non-animal sources of B12 or consuming excessive synthetic analogs may develop symptoms of deficiency despite meeting intake recommendations and achieving normal blood concentrations. The body's ability to transport and absorb B12 also varies greatly among individuals. Absorption requires a multi-step process involving gastric acid, intrinsic factor, and receptors in the ileum, all of which can be impaired by age, medication use, such as proton pump inhibitors or metformin, genetic polymorphisms, or autoimmune conditions like pernicious anemia. Even mild gastrointestinal dysfunction can disrupt this intricate system and lead to a subtle, cumulative shortfall in intracellular B12 that may not be immediately apparent on a lab report. The brain and peripheral nerves, due to their high metabolic demands and reliance on B12-dependent methylation for structural upkeep, are often the first systems to suffer. Because of these nuances, a growing number of researchers advocate for more sensitive and functionally relevant markers of B12 status. Two such markers, methylmalonic acid, MMA, and homocysteine, rise in the presence of functional B12 deficiency and offer earlier insight into metabolic imbalance. Elevated MMA indicates that the B12-dependent enzyme methylmalonyl-CoA mutase is underperforming, while elevated homocysteine suggests insufficient methylation capacity. Both markers are intimately linked to neurotoxicity and oxidative stress when left unchecked, and they often begin to deviate before serum B12 falls below the diagnostic threshold. Clinically, this opens up important questions. Should we be screening for B12-related metabolic dysfunction in individuals with unexplained neuropathies, cognitive changes, or psychiatric symptoms, even when their blood B12 levels appear unremarkable? Should a normal B12 level be considered reliable without also measuring active B12 or functional markers like MMA and homocysteine? For many neurologists and integrative practitioners, the answer is increasingly no. They have found that supplementation, especially with methylcobalamin, the neurologically active form of B12, can relieve symptoms and slow progression in cases where standard labs showed nothing unusual. The therapeutic window here is critical. Early intervention with high-dose B12, whether oral, sublingual, or intramuscular, can often reverse or stabilize neurological symptoms. But the longer a subclinical deficiency persists, the greater the risk of permanent damage. This is particularly relevant for older adults who often experience a gradual decline in B12 absorption, and for those with conditions like diabetes or multiple sclerosis, where nerve health is already compromised. What makes B12 uniquely promising is its safety. It has no established toxicity threshold, allowing generous repletion without risk. In sum, the disconnect between blood levels and neurological health in B12 status challenges the conventional paradigm of nutritional testing. It reminds us that numbers on a lab sheet do not always reflect biological reality, especially in complex systems like the nervous system. B12 may be present in the bloodstream, but if it is not being transported, absorbed, or activated at the cellular level, it might as well not be there at all. This subtle but dangerous gap between biochemical presence and biological usefulness is where hidden nerve damage can begin, silently, and persist until the fog of symptoms prompts deeper inquiry. It's a vivid reminder that in nutrition, as in neurology, what you cannot see can still harm you, and what you act upon early may be your best defense against slow, silent decline.